How do we calculate now properties? Well, we could calculate them as those derivatives, but that requires two or three things. It requires, first of all, that we have some kind of strategy for calculating the energy in the presence of fields, because that's what we need here in order to take the derivatives. So we need some kind of way of doing that. And one of the ways of doing that obviously is the perturbation theory, which we had last week, so which we're going to use now again. Where here the perturbation is now not the electron correlation, the instantaneous electron correlation represented by the fluctuation potential, but now it's an external magnetic field or an internal magnetic field coming from magnetic moment. The second thing is then, which in a way comes before, is how do we incorporate those perturbations in our Hamiltonian? Because I mean, in perturbations here we split our Hamiltonian up in the unperturbed Hamiltonian plus the perturbation. But the case we looked at, which was electron correlation, there we sort of, I mean, we had the full Hamiltonian, we only had to split it up in a part which we could solve, and then the rest which we wanted to treat as a perturbation. But we don't know a priori yet how a Hamiltonian looks like when we have some fields present. So the first big question is, how do we get the fields in the Hamiltonian, or what is the Hamiltonian with fields? The Hamiltonian with external or internal fields. Now the approach we and basically everybody else is taking there is sort of a semi-classical approach, and it's also what is called a minimal coupling. Semi-classical minimal coupling. Because what we do is when we use classical expressions for the fields, classical electromagnetism expressions, and not quantum electrodynamics, I mean, the proper way would be to do QED. Quantize the fields as well as the electrons. And some people started to do that. I mean, there are some research groups who are doing that and looking at QED effects to properties. But that's not what we're going to do here. So we treat the fields classically, just classical electromagnetism equations we use. Whereas the electrons we treat with quantum mechanics. So it's a semi-classical, halfway is classical. And then it's a minimal coupling, because the only thing we allow then is that the fields perturb the electrons. But there's no other way around. So it's a one-way communication. And the point is then that the fields and also the magnetic moments, meaning fields coming from the magnetic moments, they enter the Hamiltonian not as fields, but actually through their potentials. And they enter in form of their potentials. Which means we have to sort of go back to as much or as little of electromagnetism we learned, and remember what is the potential for, if I have an electric field, there's a potential associated with that field, and how does that look like? So for the electric field, we have a potential coming from the electric field, and that has, I mean, this potential is also a field, so it has different values at different points in space. And that is minus, and here's the position vector where we look at which is later on going to be the position of an electron I, relative to the origin of the coordinate system, times the electric field. So that's the potential associated with the field. You probably know sort of the other way around. If you have a potential, you can get the field as the gradient of that potential, minus the gradient of that potential. Now, in a way, it's not completely new what I'm doing here, because we have already some potentials in the Hamiltonian, which are actually interactions with electric fields, because the electrons are moving in the electric field of the nuclei. There we already have a potential. That's sort of the Coulomb potential, because we have point charges, and that has but you normally don't write up what is actually the field coming from the nuclei. So you immediately write up Coulomb law, the potential. But it's in a way not different than this one here. Now we just have a uniform, for example, or a uniform or maybe an oscillating field in a few weeks when we look at frequency-dependent properties, and this is going to be a time-dependent field, oscillating field. Here it's just a static field now. And this is sort of, writing up this is just basically the fact that the field is minus the gradient of the potential. And if you go the other way around, you end up here. Similar for magnetic field. And there you have very much a corresponding equation where the magnetic field is now not the gradient, but it's the curl of the potential. And this is then a vector. Therefore, this is called the vector potential, and this is correspondingly called the scalar potential. So electric fields have a scalar potential because they are the gradient of that scalar potential, whereas magnetic fields, their potential are vector potential because the magnetic field is defined as the curl, the vector product of the gradient vector and the potential. And that is just classical electromagnetism, Maxwell equations and all that. But that means for us, if we have a homogeneous magnetic field, like here, this being a homogeneous electric field, for a homogeneous magnetic field, then the vector potential looks like this. RE minus R, like this. Where now it's not the scalar product of the position vector and the field, but it's actually the vector product of the field and the position vector. I mean the position where I want to know what the potential is. And in both cases, you have to have some kind of an origin. Well, there is an origin in there, and the potential depends on those origins. So if you change the origin, I mean, you get a different value for the potential. Now that's the external magnetic field, a homogeneous external magnetic field like you have in big NMR spectrometer. But we also need a potential for a magnetic moment. I didn't write down, yeah, let's sort of MA. Yeah, RE. And that's still the same here. So that expression for the potential has to reproduce, when I insert it in here, the expression for the magnetic field coming from that magnetic moment. And that turns out to be μ0 divided by 4 pi, the magnetic moment A, vector, cross Ri minus the position of that, where this magnetic moment is, divided by Ri minus Ra to the third power. So those are the three kinds of potential. And if the electric field wouldn't be homogeneous, but it would have also a gradient, then I sort of could extend this and add extra terms, which then instead of R would involve R squared contributions. But let's stick with that. Let's stick with a homogeneous electric, homogeneous magnetic field, and a magnetic moment.